It's time to start symbolic calculus, and we're going to start that by talking about limits of functions at a point, which we've already motivated a little bit in the previous presentation, so we can get right at the abstract meat here. The definition of the limit of a function at a point, which is an informal definition, and that's going to be good enough for what we're going to do in calculus, is that if p is a real number, p for point maybe, then the function f is set to converge to the limit L at p if and only if, for all x sufficiently close to but not equal to p, we have that f of x is close to L. In that case, L will be called the limit of the function at p. Well, that is a perfectly good mathematical definition, but what does it mean? Well, okay, notation, L is limit as x goes to p f of x. And I think now we're talking about what it means. Let's take a look at the function f of x equals x squared plus 2x minus 3 over x minus 1. The graph of that function looks like this. Well, now if we plug in values for x that are close to but not equal to 1, what we're going to see is that the output values, graphically speaking here, they're getting to be close to 4, right? And if we do that with a table, we can take values x that are close to the left of 1, like 0.9, 0.99, 0.999, 0.9999, and values that are close to the right of 1, like 1.1, 1.01, 1.001, 1.0001. And we can't plug in 1 itself, because at 1 the function is undefined, but as we get really, really close to 1, our output values get close to 4. So graphically, as well as numerically here, we see this idea of a limit is that as our inputs approach the limiting point, our outputs are supposed to approach the limit, which in this case looks very much like it should be 4. Now, the unfortunate part is that drawing these pictures, you can't just tell a computer, draw this picture for me and then give me the limit. And this kind of stuff, if the limit isn't easy, is also not very easy to guess, because if this limit had been something like square root of 15 or so, the digits may not have been very suggestive as to what the limit is. So we need something to allow us to compute limits, and that's the limit laws, which consist of elementary building blocks as well as ways in which limits connect with the algebraic operation. The elementary building blocks are, we just look at p being our point where we compute the limit, and let c be a real number. Then the limit as x approaches p of c is c. Well, as x gets close to c, as x gets close to p, where does c go to? Well, c is a constant. It's a horizontal line, so it's already there. The limit is c. Well, duh. And the limit as x approaches p of x is p. That sounds like one of those silly questions that is just too easy to answer. What does x approach as x approaches p? Well, it approaches p, of course. Then the connection, the algebraic properties of limits are that if f and g are functions, so that the limits of f and g both exist, and if r is a real number, well, then the limit of f plus g of x as x approaches p is the limit of f plus the limit of g. The limit of f minus g is the limit of f minus the limit of g. The limit of f times g, you guessed it, is the limit of f times the limit of g. The limit of f divided by g, you guessed it, is the limit of as x approaches p of f divided by the limit as x approaches p of g. And that, of course, only works when the denominator is not equal to 0, and we'll have to work our way around that in just a second. And the limit of a power of the function, the limit of f to the r, is the limit of f quantity raised to the rth power. So basically, algebraic operations just factor through limits as long as the operations are allowed before and after. All right, so let's go back to this function x squared plus 2x minus 3 over x minus 1. Near x equals 1, the graph gives values near y equals 4. And that's the picture here. Remember how I said in the introduction you want to have the visualization behind the words. I'm trying to just flash the pictures to give that visualization back. The table of input values versus output values also suggested that the limit should be 4, and that was the table of input versus output values, right, suggests that there ought to be a 4 in here in this column. But the limit laws cannot be applied because at x equals 1 we divide by 0. So we have to get rid of the division by 0, and of course that was always the idea behind limits. But so note that except at x equals 1, we have that x squared plus 2x minus 3 over x minus 1 is equal to, well, just factor the numerator as x minus 1 times x plus 3 divided by x minus 1. And that's, of course, equal to x plus 3, except at x equals 1. And for the limit, it should not matter now that the two expressions are not equal at x equals 1, because the definition of the limit specifically says that we're only interested in what happens near the limiting value. And, well, near 1, this thing is equal to x plus 3, and 1 plus, therefore, it would be approximately 1 plus 3, which would be 4. The next theorem now really guarantees that within reason we can replace functions with nicer functions. It's a little bit technical, but hey, we let p be the number where we compute the limit. We let f and g be functions defined at least on an interval around p. Basically, you can take a little step delta to the left of p, you can take a little step delta to the right of p. P itself is excluded. This sign here is minus for sets, so we're excluding p specifically. So these functions are defined on an interval around p from which p was removed. And if for all points x in that interval from which the center has been removed, if for all those points f of x is equal to g of x, well, then the limit as x approaches p of f is equal to the limit of f as x approaches p of g. This equation should be read as either both quantities exist and they're equal, or neither one of them exists, because, well, basically, for all intents and purposes for the limit computations, these two functions are the same, so either both limit exists and they're equal, or the function blows up either way. Okay, so now we can actually compute that limit with algebraic methods. We take the limit as x approaches 1 of x squared plus 2x minus 3 over x minus 1. And that's the limit as x approaches 1 of x minus 1 times x plus 3 divided by x minus 1, which is the limit as x approaches 1 of x plus 3. And that's just 4, of course. Okay, now one thing, and this is maybe a pet peeve of mine, but anytime we do this kind of factoring where you basically guess how a quadratic factors or so, that only works for problems that are rigged. Now, most problems in a calculus class are rigged, but there is a way to avoid this kind of factoring, which I deliberately put in quotation marks. I mean, anytime you've got a quadratic that factors, that's wonderful, but that's an accident. We all know that quadratics can have really ugly zeros, which would have to be computed with the quadratic formula. So there is a way to do these computations in a bit more reliable a fashion, and by avoiding this kind of factoring, and that's this theorem. Again, we've got that number, that place where we're going to compute the limit. We've got a function that is defined on this interval from which the center was removed. And then the limit as x approaches p of f of x is the limit as h approaches 0, f of p plus h. Well, let's see, how does this go? When h goes to 0, p plus h goes to p, so that ought to be the same thing. And the proof is a little technical, but it works out. The limit as x approaches p of f of x is the limit as x approaches p of p plus x minus p, right? That's the same thing, because p minus p, that goes away. A teaching assistant who taught me when I was about your age once said, there are only two tricks in mathematics. One is adding 0 and the other one is multiplying by 1. So here we've added 0. That's the limit, of course, now. When x goes to p, then x minus p goes to 0, of the same thing, f of p plus x minus p. And now we just rename x minus p to be h, so this is the limit as h goes to 0 of f of p plus h. And that's already the proof of the whole thing here. With that, we can compute more complicated limits. Now this one I think can also be computed with factoring, but like I said, I'd like to have a method that works for all sorts of ugly stuff. And in this example section, we're going to work our way up to some pretty ugly stuff, and that's deliberate, because if you can do the really ugly stuff, you ought to be able to do everything. Okay, so let's take the limit as x approaches negative 3 of x squared plus 4x minus 3 divided by 2x squared plus 2x minus 12. That's the limit as h goes to 0 of negative 3 plus h squared, that's the x squared, plus 4 times negative 3 plus h, that's the 4x, plus 3, well, that's just the 3, divided by 2 times negative 3 plus h quantity squared, that's the 2x squared, plus 2 times negative 3 plus h, that's the 2x, minus 12, well, that's just copied. That's equal to, well, now we just have to multiply out parentheses. We always have to do some kind of algebra, but remember, it's just algebra. We can do this. Negative 3 squared is 9. 2 times negative 3 times h is negative 6h, and h squared is h squared. 4 times negative 3 is negative 12. 4 times h is 4h. 3 is copied down. 2 times negative 3 plus h quantity squared. Well, negative 3 squared is 9 times 2 is 18. Negative 3 times 2 times h is negative 6h times 2 is negative 12h. H squared times 2 is 2h squared. That takes care of this parenthesis here. 2 times negative 3 is negative 6. 2 times h is 2h, and the negative 12 is copied. And now we can cancel a bunch of stuff, right? 9 minus 12 plus 3 is 0. 18 minus 6 minus 12 is 0 also, so we'll not have any constant terms. Numerator will be h squared minus 6x plus minus 6h plus 4h, so that should be h squared minus 2h. The denominator should be 2h squared minus 10h. Ha! And I got it right. You can see here, you want to be able to do this kind of stuff mentally, and you want to either be able to predict what's going to happen or verify what has happened. And here, from the first to the second line, I've shown you how to verify that everything was correct, and from the second to third line, I've shown you how to predict what's going to happen. Well, now here we can factor out an h in numerator and in the denominator, so that becomes the limit as h goes to 0 of h times h minus 2 divided by h times 2h minus 10. So that's the limit as h goes to 0 of h minus 2 over 2h minus 10. And that's negative 2 over negative 10, which is 1/5. Somewhat hairy computation in the middle. Now do not be shy if worst comes to worst. And if that part here, that was probably the ugliest step in between, if that part here just didn't work for you, or if it doesn't work for you as you read something in a book, just get yourself some space on the paper, or get a separate piece of paper and work it out. 2 times negative 3 plus h squared is 2 times 9 minus 6h plus h squared. That's just a binomial formula. You multiply that by 2, you get 18 minus 12h plus 2h squared, and that's exactly what we have here on the bottom. And that is something that can be done for any computation. If there is a piece in a computation that you don't quite see right, get some paper or just work it out in the margin, but work it out. The idea here is not for you to try to read this fast or try to listen to this really quickly to impress yourself. The idea is to make sure that this works. Okay, we can also check whether that limit is right, and we can do that graphically, because we can just graph the function, including the hole that exists at negative 3. And then we can just draw the horizontal line 1/5, and 1/5 is a little bit less than 1/4, so that is the line 1/5 here. And that line ought to go exactly through the hole right here, provided that the limit is correct. If that line was somewhere else up here, we would have to double check the computation, because something would be wrong. Okay, let's look at a harder limit, the limit as x goes to 8, x minus 8 divided by root x minus root 8. That's the limit of 8 plus h, that's the x, minus 8, just copied, over the square root of 8 plus h, which is the square root of x, minus the square root of 8. How do you get rid of square roots? You get rid of square roots by expanding, by rationalizing, and so here we are, well, we're first going to simplify. 8 minus 8 goes away, but that's the only thing that has happened here. How do you get rid of the square roots? You get rid of the square roots by rationalizing. So we expand with the conjugate of the denominator, square root x plus h, square root 8 plus h plus 8 in numerator and denominator, right? There are two tricks in mathematics. We've already seen the adding 0. Here we're multiplying by 1. And, well, if these roots were in the numerator, well, then we would be rationalizing the numerator, no problem there either. As we do that, okay, we leave the numerator as is. This is the limit as h goes to 0 of h times square root 8 plus h plus square root 8, divided by, and in the denominator, where we get the square of the first minus the square of the second, so we get 8 plus h minus 8. And that's, of course, where 8 plus h minus 8, where the 8's go away. So this is the limit h times square root 8 plus h plus square root 8 divided by h. And here's where we didn't want to multiply things out, because now we can see the cancellation of the h's very quickly for the numerator. So this is the limit as h goes to 0, square root 8 plus h plus square root 8. That's square root 8 plus square root 8, because h goes to 0, and that's 2 times square root 8, which is 4 times square root of 2 if you take out a square root of 4 here. And that's approximately 5.6569, and that's something we can check. We graph the function. I've already zoomed in on the area 8 versus 5.65 something. And then, of course, if you put that horizontal line, and it really goes exactly through that point, that is the hole in the function. That's an indication that we got the limit right. Now let's take a look at the limit of x squared plus minus 5x plus 6 over x squared minus 4x plus 4 as x goes to 2. Well, again, we just replace the x's with 2 plus h's. That's all that happens in this step. We've seen that before now. We multiply out the parentheses. 2 plus h squared becomes 4 plus 4h plus h squared. Negative 5 times 2 is negative 10. Negative 5 times h is negative 5h. 6 is copied down. 2 plus h squared is 4 plus 4h plus h squared. Negative 4 times 2 plus h is negative 8 minus 4h plus 4. And now again, the constants we hope will cancel, and indeed they do. 4 minus 10 plus 6 is 0. H squared copies down. 4h minus 5h is negative h. 4 minus 8 plus 4, the constants are gone. 4h minus 4h is gone. H squared is the only thing that survives in the denominator. We cancel as many h's as possible. We've got the numerator being h times h minus 1 divided by h squared, which means that this is actually the limit as h goes to 0, h minus 1 divided by h. And that's a problem, because that limit does not exist. And that is a valid answer in a limit computation. Some limits do not exist, and if we look at this graphically, the graph of the function has a singularity at x equals 2. So there is a vertical tangent line there, and that is a typical situation in which a limit does not exist. Okay, let's look at an ugly limit. Limit as x goes to 9 of x minus 9 divided by x squared minus 9 plus root 3 times x plus square root of 243. That's horrible. That's something that you certainly wouldn't want to tackle with factoring, but by replacing x with 9 plus h, things are actually going to work out fairly simple. It's going to reduce itself to algebra, and let's always remember, it's just algebra. We can do that. So, replacing x with 9 plus h is the only thing that has happened here. Now in the numerator we can cancel the 9's. In the denominator we have to multiply a bunch of stuff out. Numerator remains h. 9 plus h squared is 81, is 81 plus 18h plus h squared, right? 9 squared plus 2 9h plus h squared. Then we multiply out the other parentheses. 9 times 9 is 81. We've got a negative sign from the front. Then we've got a 9h with a negative sign from the front. We've got a root 3 times 9 with a negative sign from the front. And we've got a root 3 times h with a negative sign from the front. And then we've got a root 243 left here. Okay. Now we simplify. And what do we get? Well, we still have a root h. We've got an h in the numerator. And we've got 81 minus 81. That goes away. 9 times root 3 is square root of 243, because 243 is 3 times 81. So that goes away. So we have no constant terms. That's nice, because anytime we want this kind of cancellation in the denominator, we must not have a constant left in numerator or denominator. Then we've got 18h minus 9h. Well, that's 9h. We've got h times root 3 with nothing paired up, so that's minus h times root 3 still. And we've got the h squared from here. Now we factor out an h in the denominator just to make absolutely sure we're allowed to cancel. And that gives us that this is the limit as h goes to 0 of 1 over 9 minus root 3 plus h, and that's 1 over 9 minus root 3, which is approximately between a 7th and an 8th. I don't think I've got the decimal here. But if we check that, well, we graph the function, we realize there's a hole at x equals 9. Here's where the hole is. And like I said, 1 over 9 minus root 3, that's between 1/7 and 1/8. And if you're between 1/7 and 1/8, then you're a little bit bigger than 1/8, so you're a little bit bigger than half of a quarter, but you're not very close to a quarter, so the horizontal line ought to be about here. And again, the double check is yes, the limit does work out. Okay, now we're going to jump on the parameter bandwagon. This is the first time we're doing that, at least in the calculus part here. And anytime we do that, let me just remind you, even though this stuff is hard, and some of this stuff can be rather frustrating, and we have to keep track of even more symbols, we're working with parameters because that's ultimately where we're headed. We'll ultimately work with problems that involve more than one variable. For example, the universal gas law that you may have seen right now in a parallel physics or chemistry class is pressure times volume is equal to molarity times universal gas constant times temperature. That's 5 variables right there. So if we just play with y equals f of x and only deal with 2 variables, we're really not doing ourselves a favor, because ultimately as we apply this stuff, we need a lot more variables. And if that's not bad enough, the van der Waals equation, which is a correction to the universal gas law, actually gives you that p plus nu squared times a divided by v squared times v minus nu b is equal to nu RT. So that contains even more variables than that, and it's more complicated. So we've got to be able to handle stuff like that. And we need to be able to do that because it's a more accurate model, right? It doesn't matter whether it's pretty or not. If it accurately describes nature, that's what we have to deal with. We also sometimes deal with harmonic oscillators, and the frequency of a harmonic oscillator of a spring mass system is F equals 1 over 2 pi times the square root of the spring constant divided by the mass. And the differential equation for that is mass times second derivative of displacement plus friction constant times velocity plus spring constant times displacement equals outside forces. If those things currently don't make sense, if you haven't had that, don't be bothered by it. The idea is I just want to show you that there's an awful lot of neat stuff that we can describe, but we need to be able to work with more complicated equations. Finally, even if we just work with numbers, would you rather work with the symbol pi, or would you work with 3.141592535897993? I'd rather work with pi. Okay. Other things, parameters will ultimately then also make our solutions applicable to more problems. For example, you've worked with parameters in algebra. You can describe the graph of any quadratic function, f of x equals a times x minus h quantity squared plus k squared, because you know what h and k mean. We can optimize the surface area of a rectangular box for any fixed volume rather than for one situation where the volume is given by a number, for one box where the volume is given by a number, which is something that makes design more easy. Of course, this is a fictitious situation here, but if you can design something with the parameters, then you can easily adjust your model. And the thing then is solving more routine problems of the type that we've seen in examples, and yes, ultimately you will consider these things routine problems. That's not the answer to get ready for parameters. We've got to be able to work with the parameters themselves. And, well, on the other hand, also, routine problems are what computers are for. Basically, you parameterize, so we work with parameters, you parameterize the problem and then you program it. So this is also something that ultimately will absolve us of doing a lot of the stuff that is plunk and grind work in a class like this one. Finally, you also gain deeper insights by solving harder problems, because you work with more complicated symbols, you see a little bit more how things arrange themselves, and that's of course the purpose of this stuff here. We want to be able to tackle more complicated problems, but we also want to be able to work harder computations. Okay, so here this is obviously a made-up problem. We want to find the value for the parameter a so that the limit as x goes to 3, x squared plus ax plus 6 over x minus 3 exists. Well, okay, so here's the limit. We plug in 3 plus h, and we multiply everything out, right? 9 plus 6x plus h squared here. We capture the square also. That's just the 3 plus h quantity squared. That's just binomial formula. A times 3 plus h is 3a plus ah. 6 is 6. And 3 plus h minus 3, well, that's just h. Now we simplify. H squared stays with us. 6h plus AH is 6 plus A quantity times H. 9 plus 6 is 15, and 3A stays with us, and we've got an H in the denominator. And here's where we now have to draw on our symbolic knowledge. H can cancel with something in the H squared. H can cancel with the H here. H cannot cancel with the 15 plus 3A. So for the limit to exist, we must have that 15 plus 3A is equal to 0. And that means we need A equals -5. That's the one value for which this thing is not 0, and therefore this is the one value for which the limit exists. So that's the answer. The value for A is A equals -5, but now we might as well figure out what the limit is, because now that we have that, when A is -5, like I said, this stuff goes away. 6 minus 5 is 1, so you just end up with H squared plus H in the numerator divided by H in the denominator. Factor out the H in the numerator, cancel it, we get the limit as H goes to 0 of H plus 1, and that's equal to 1. So not only have we found that we need A equals -5, but we have also found that the limit in that case is equal to 1. Okay, we conclude with a conceptual tool, which is the squeeze theorem. It is a theorem that isn't used very often because you need to have a very special situation, but when you need it, it definitely is needed. And so, well, what's the theorem? If f, g, and h are functions that are defined on this interval that we've hopefully gotten used to by now, little wiggle room to the left around p, little wiggle room to the right around p, but we don't care what happens at p itself. And the functions need to satisfy on that set that f is below g, which is in turn below h. Then if the limit of f is the limit of h, and that limit is L, then the limit of g is L too. Basically, the function g is squeezed between f and h, and if f and h both go to L, then g has no choice but to go to L also. We'll see a visualization of that in the example that we're about to work. Namely, we're looking at the limit as x goes to 0 of cosine 1 over x. Well, hey, when x goes to 0, you got an x here that's 0, and 0 times anything is 0. But cosine 1 over x, we don't know what that does, and in fact, it oscillates like crazy. So we have to be a little bit careful, because 0 times anything doesn't always work out to be 0 when we talk about limits. Pretend the cosine isn't there. If this was x times 1 over x, well, x times 1 over x is 1, and the limit would be 1. Okay, that's not the problem here. We're interested in the limit of x times cosine 1 over x. That was just a reminder. We have to be careful. Well, we can simplify, we can cancel, but what we do know is that x times cosine 1 over x is bounded above by x absolute value because the cosine is less than or equal than 1. X times cosine 1 over x is bounded below by negative x absolute value because the cosine is greater or equal than -1, and so then x is greater or equal than negative x absolute value here. And the limit as x goes to 0 of x absolute value is 0, which is also the limit as x goes to 0 of negative x absolute value. And so by squeeze theorem, the limit as x goes to 0 of x cosine 1 over x is equal to 0. And if you're good with symbols, then all that stuff works out. Let's take a look at this graphically also. Here's the function, and you can see that there are actually infinitely many oscillations that are squeezed between -0.2 and 0, as well as between 0.2 and 0. That's because 1 over x goes to infinity as x goes to infinity, so the argument of the cosine function goes to infinity as x goes to 0, and that means all these oscillations that the cosine function does on the positive axis all the way out here, they are wrapped into the interval between here 0.2 and 0. So this thing oscillates like crazy, but it is bounded above by the function x absolute value. And we really couldn't just say x here because for negative signs everything reverses, right? So that's why we needed the absolute value here. It's bounded below by negative x absolute value, and we now can see here what the squeeze theorem does. It basically, the function above and below the function that we are interested in, they define some kind of a funnel, and no matter how crazy the function acts within that funnel, as we approach the point where we're interested in the limit, the function must approach the same limit as the upper function and the lower function do. And, well, that was the squeeze theorem. That was our introduction to symbolic computation of limits. Remember, the algebra may get ugly, but it is just algebra. Work some problems and move in your exploration of limits. I'll see you in the next presentation.